In the previous video, we have discussed about what is structural analysis and what is structural design and all about structural members. In this video, let's see how do we choose the preliminary size of structural member. To design the concrete element, the design engineer has to determine the loads to proceed with the design works that require calculating the dimensions of concrete member. So whatever the structure we design, we should know the dimensions of the structural member. The size of the member shall be fair enough to withstand the loads which is coming on the particular member. As I told you before, the external loads will be applied on the structure that is in the structural members. So whatever the members we choose, the size of the members shall be fair enough to withstand the loads which is coming on that particular member. It is very important to estimate the preliminary size of concrete element. Self weight is one of the significant loads that a structure must support, and it requires dimensions of the concrete member. So apart from the externally applied load, whatever the dead weight, that is the self weight, right? So if it is a column, it has its own self weight. If it is a beam, it has its own self weight. So for that also we need the size. Without knowing the size of the member, we cannot arrive the self weight of the member. The major purpose of structural design is to determine the geometry and reinforcement area for the structural elements. Primary sizes are not exact one, but we can assume the values as per thumb rules, and codal provisions reduce the extensive iteration of the calculation procedure. So as per thumb rule, we can assume the preliminary size of the structural member and we can go ahead with the analysis procedure. After analyzing the structure, we can just do the design, and then we can check with the code whatever the permissible limits are there according to the code. So if it is satisfying the code, then we can proceed with the size whatever we have taken, or else we have to revise the size and then do the procedure again. First, let's see how to choose the initial size of the slab. So in IS 456-2000 class number 23.2.1, the span to depth ratio is given. Basic values of span to effective depth ratios for span up to 10 meter. For cantilever it is 7, for simply supported it is 20, for continuous it is 26. So this value we have to consider and we have to choose the initial size of the slab. The next condition is for span above 10 meter, the values in A may be multiplied by 10 by span in meters except in cantilever, in which case deflection calculations should be made. So this is one condition. Another one is depending on the area and the stress of steel for tension reinforcement, the value in A or B shall be modified by multiplying with the modification factor as per figure number 4. So this is the figure number 4, modification factor for tension reinforcement, and figure number 5 is the modification factor for compression reinforcement. So this formula we have to use. Fs is equal to 0.58 Fy into area of cross section of steel required divided by area of cross section of steel provided. So from this table we can see basic values. Span to effective depth ratio for span up to 10 meter, for cantilever it is 7, simply supported it is 20, continuous it is 26. Next, modification factors for spans greater than 10 meter. This is not applicable as deflection calculation should be made for cantilever. Next one is simply supported and continuous. Multiply values of rho 1 by 10 by span in meters. If the modification factor is greater than 10, we have to multiply these values by 10 by span in meter. Modification factor depending on area of stress of steel, then we have to multiply the values of rho 1 and 1 or 2 with the modification factor from figure 4 of IS 456. Modification factors depending as area of compression steel, further multiply the earlier respective value with that obtained from figure 5 of IS 456-2000. As per IS 456-2000, the minimum percentage for HYSD bars is 0.12%. That is the minimum reinforcement we have to provide for slabs which is having HYSD bars. So here I have taken 0.2%. So for this 0.2% and this Fs value, we need to find out the modification factor. As like beam, slabs also will be having tension reinforcement at bottom and compression reinforcement at top. So here let's take this figure 4, modification factor for tension reinforcement. The percentage of tension reinforcement assumed is 0.2. So that comes here, and the modification factor we need to find out. Fs value we have calculated as 240. So 0.2 is the value of percentage and Fs is 240. So for this we have to find out the modification factor. it comes around 1.6. So let's take this value as a modification factor. From the chart, we got the modification factor as 1.6. Before proceeding with the calculation, let me tell you about what is overall depth and what is effective depth. Here I took the beam for better illustration. The same concept will work for slab as well. Overall depth is the full depth of the beam or slab. Overall depth is equal to effective depth plus dia by 2 plus clear cover. So this is the formula to calculate the overall depth. Similarly, if you want to calculate the effective depth, you have to deduct clear cover and dia by 2 from overall depth. So this is the concept behind effective depth and overall depth. Clear cover is the cover which we provide for each and every structural member. So that is different for all the structural members. Clear cover for slab is 15 mm. Span to depth ratio is equal to 20 multiplied by modification factor. We know the modification factor value as 1.6 and span is 3.5 meter, 3500 mm. So always you have to consider the shorter span. So 3500 divided by 32, which gives your effective depth, that is 109.38 mm. Overall depth is equal to, as I told you before, effective depth plus clear cover plus dia by 2. Here let's assume 10 mm dia bar. Overall depth is equal to effective depth plus clear cover for slab is 15 mm plus 10 by 2. 10 is the dia of the bar, 10 by 2. So overall depth we get as 130 mm. From this again we can recalculate the effective depth. So effective depth is equal to overall depth minus clear cover minus dia by 2. We get 110 mm.